as you have already seen, in discussing flow of materials, it is important to talk about stress rather than simply talk about force. And as you know, force is a vector, a concept that I think many of you are quite comfortable with already. But stress is a tensor, a concept that I think is not new to you, but you haven't probably dealt with in as much detail as you have vectors. So today what I'd like to do is use this short video to talk about tensors and do that in the context of starting with talking about scalars, moving on to talking about vectors, and then talking about tensors. And we'll see how they're all part of the same class of properties for a material. So returning to this slide that we've used before, we've talked about stress. We said it's what drives or causes deformation. And we've talked about strain, which is the response to the stress. And the question that we want to talk about today and in the next video is how do we relate the stress to the strain? How do we couple the two? If stress causes strain, then how do we link the two? How do we know how much strain we're going to get if we apply a certain stress? And to do this, I want to build a little bit of background in talking about tensors. And we're going to talk about scalars, vectors, and about what you think of as tensors. So a scalar is a quantity, according to Wikipedia, that is independent of a specific coordinate system. So I'm not going to introduce coordinate systems quite yet. You're familiar with scalar quantities or things like mass, temperature, density of material, time, and so on. In terms of tensor notation, we call these zero-rank tensors, and they have a single component. And one way to think about the title of zero rank is that if you were to take a scalar and shrink it down as small as you could, it would become a dot. Therefore, it would be a zero-dimensional quantity. And mathematical operations you're all familiar with. Two of the simple ones, you could do multiplication or you could do addition and so on. And you're all, I think, very comfortable with those type of operations. When we talk about vectors, vectors have both a magnitude and a direction. And they're very coordinate specific. And so I'm going to set up a coordinate system in the lower right part of the screen here. And we'll use a Cartesian coordinate system that you should hopefully all be comfortable with, where we have three axes mutually orthogonal to each other, x1, I'm going to call them x1, x2, and x3. Could have called them x, y, and z, but you'll see in a moment why using the subscripts 1, 2, and 3 turns out to be really a valuable approach for doing this. Okay, four common vectors. The one we've been talking about in class is force. Velocity is a vector. It has both a direction and a magnitude. A common one that I like to talk about ultimately, and we'll talk about later in the class, is flux. We'll talk about how much water flows down a stream, what the flux of material is. Tensors, in tensor notation, vectors can be called a first-rank tensor. They're described by three numbers, and they can form an array, either a 1 by 3 horizontal array or a 3 by 1 vertical array. And we'll see those terms and concepts crop up in a few minutes. And we can look at force as a vector. I've drawn it here on top of my Cartesian coordinate system. Here's the force vector over here, and we can break it down into components F1, F2, and F3, which are the projections of that force onto three mutually orthogonal coordinates. And we can write that force in many ways. The way I like to show forces, I write it the F for force, and I put a little tilde underneath to indicate that it's a vector. And I can break it out into its three components, F1, F2, and F3, written as multiplying by the unit vectors in the 1, 2, and 3 directions. And it's often written again as an array, as I set up here. And we could write that out as three components, F1, F2, and F3. So they're all the same notation, or all the same concept, just written out in different notations. Vectors are a little bit more challenging to deal with mathematically. There are two common operations that you'll need to deal with. One is the dot product, where you simply take a vector 1, 2, 3, dot it into the vector 4, 5, 6, And you get the result by taking the 1 times the 4, gives you the 4. The 2 times the 5 gives you the 10. The 3 times the 6 gives you the 18. And you end up, if you add them together, with 32. Cross products are a little bit more challenging, but I think all of you have dealt with them recently in your math classes. And if we take two vectors, u and v in this case, and we make a cross product between them, and I'm going to take a specific example where I set the x3 component, the coefficient in front of the x3 term, to be equal to 0. So I have two vectors that look like u1, u2, 0, crossed into v1, v2, 0. And the way I learned to do this, and I think useful visually to do this, is to set this up as a determinant. And since there are zeros over in the x3 column, I only have to worry about multiplying x3 times u1 times v2 minus u2 times v1. And that's multiplied by the x3 direction. And it gives you the result that you've learned to expect already, that the two vectors that you give form a plane, and the cross product gives you something that's normal to that plane. Okay, so hopefully all of that's reasonably familiar to you. Now we want to talk about tensors, which is where we dig into talking about our quantities, stress and strain, which are important topics in this class, and later on we'll expand this to strain rate. So tensor, we're going to talk about these as second rank tensors, or often they're just, the second rank is dropped and you simply talk about tensors, but later on we're going to talk about fourth rank tensors. So we want to kind of in the back of our mind keep in track of the fact that this is in fact a second rank tensor. And basically a tensor links two vectors. And the vectors we're going to link are things like forces and areas. So in tensor notation, we're talking about second rank tensors. They're going to form a 3 by 3 array, so they're going to have 9 components. And it's second rank in the sense that if you shrink this down to a small size, you always are left with a plane, a two-dimensional object, and therefore it's called second rank. And an example of a tensor that you've already been introduced to is the stress tensor. The way I'm going to denote these here and in class is I'm going to put 2 bars underneath the sigma to indicate that it's a tensor. And if we write out it in terms of component, again, it's a 3 by 3 array. And we'll write it as sigma 1, 1, sigma 1, 2, sigma 1, 3, etc. The terms down the diagonal are 1, 1, 2, 2, and 3, 3. And it has 9 components, as we said it would. And the components, again, are referenced back to our coordinate system. So the 1 refers to the x1 direction, the 2 subscript refers to the x2 direction, and the 3 subscript refers to the 3 direction. And we'll come back and look at these much as we did earlier in a previous lecture. We'll look at these reference to stresses on a cube. Okay, so here we are. Here's our cube. We saw this in an earlier lecture. It has the coordinate systems x1, x2, and x3. We're going to look at, primarily in this case, we're going to look at the front face of this cube, the one that has an area A1. It has a normal in the one direction, unit vector in the one direction. What I want to do in this case is we're going to couple two concepts that we've talked about. We're going to look at this force vector, and we're going to use it. We're going to try to calculate the components of the force vector in terms of the area vector for this face, and in terms of the stresses, sigma 1, 1, sigma 3, 1, and sigma 2, 1 operating on that face. And I want you to recall we defined how we handle stress terms last time. We're going to talk about sigma ij, where I and j both go from 1 to 3, representing the 1, 2, and 3 coordinate system. And I want to calculate the force vector obtained by multiplying the stress tensor times the area vector. Okay, so the area vector for this particular face only has one component. Its normal points out in the one direction. Okay, it has an area equal in magnitude equal to A1, has a unit vector in the one direction. And so I can write this product as this area vector times the stress tensor, and I want to calculate the force components. And so let me calculate first the F1 term, and I get that by taking this top row of the stress tensor, and you can think about rotating it 90 degrees and calculating the force. You're going to take the sigma 1,1, multiply it by A1, sigma 1,2 times 0, sigma 1,3 times 0. And if I do that, I'll end up with the force in the one direction is just sigma 1,1 times A1, all right, which hopefully is logical to you. Here's sigma 1,1, and it's operating, in this case, compressively on A1, and the normal force then is equal to sigma 1,1 times A1. I can calculate the effect of one of the shear stresses, and I'm going to specifically look at the shear stresses again on the A1 face, and I'm going to try to calculate the 3 component of my force over here, and I'm going to take the third row of my stress tensor, again rotate it through 90 degrees, multiply it by the area vector, basically doing it, in your mind you can think of doing a dot product. And so F3 is equal to sigma 3,1 times A1 plus sigma 3,2 times 0 and sigma 3,3 times 0. And so I get back just sigma 3,1 times A1. So it's exactly what you'd have done if you'd just done it by intuition. I took this vector, or the stress component sigma 3, a shear stress, operating in this A1 plane, multiply it by the area, and I get back the force in the 3 direction. And again, the 3 direction is the vertical direction. So this stress here operating in the vertical direction gives me back a force, F3, operating in that direction on the front face. So all these forces are operating on this front face of the cube, the one that has normal to the x1 direction. Okay, now what we want to do is take the next step. So we've linked stresses, or used stresses to link forces and areas. So we use a tensor to link 2 vectors, and now we want to talk about linking 2 tensors. And we talked a little bit about this in class. In physics, we use Hooke's law to describe the force vector and its relationship to displacement. And the way I like to think about it, and I think the physical way to think about it, is that a force applied gives rise to an extension. In mechanics, you go from forces to stresses and strains, forces and displacements to stresses and strains. And so we would write out, in mechanics, you'd write out the strain is equal to the stress divided by, in this case, what's called the Young's modulus. And we talked a little bit about Young's modulus already, and I'll talk more about it in a few minutes. And we talk about shear strains produced by shear stresses, and the term that couples those two is called the shear modulus, written as G. Okay, but we've already seen that stresses and strains aren't scalars. They're in fact tensors. And so we're stuck with this problem. How do we relate two tensors to each other, right? We have both second rank tensors. We have the strain tensor on the left, the stress tensor on the right. And I want to know, how do I go, if I know the stresses, how do I calculate the strains? And that is not such an easy problem, but it turns out not to be as complicated as you might initially think. But we need something that couples in between, much like we had a second rank tensor coupling 2 vectors. We need something, some tensor or some product, something that goes in between here that couples the stresses we apply to the strains that result. We'll come back and talk about that in a few minutes. Some useful resources that you might look up, and there are a lot of other ones out there, but a couple that I looked up on YouTube are listed here that talk about vectors and tensors, and talk about, one of them talks specifically about the stress tensor.